Okay, so good morning everyone. In this video, I am going to discuss one application of priority queues with heaps. And one of this is the heap sort, or an algorithm to sort an array of n elements by turning the array into a heap, then doing a remove operation n times. So essentially, the elements will come out in assorted no order. Why? So what we do is we have a heap, right? And we know that a heap follows two properties. One is completeness and the other one is the heap ordering. Wherein in a heap, we always know that the parent will be less than or equal to its child. And in a mean heap, we know that the root will always be the minimum. So what we can do is every time we remove the root because that's the minimum. And after removing that root, rebuild the heap, fix it, and then remove the mean again, and so on until we have um, checked all the possible nodes. So essentially, every time we remove a mean, we can put them in a new sorted array. Okay, so what would be the runtime then? So the heaps the heaps should have been shown have been minimum heaps because the elements come out in the ascending order. So if we use a max heap instead, so it would just be the same thing, but the elements would be in this descending order. So in this case, in the max heap, the parent will always be greater than or equal to its child. So essentially, the root will have the maximum na value. Okay, so this is an example of a max heap. So in this case, the 9 is greater than 7 and 5, and then the 7 is greater than 2, and then 6, and then 5 is greater than 4. Okay, and if we perform a sorting in a max heap, so essentially what we do is we know that the root is the maximum. So we are going to swap 9 with 4, right? 9 with 4. And then the 4 would then be on the root, and then 9 would be removed. And then this uh, 9 would be can be put in a new na sorted na array. And we are going to do this again by putting the 7 as the root and then remove it again and add it into the new sorted array. So that's what we can do with heap sort and with using a max heap. Okay, but there is an improved na heap sort. And initially, in the first na algorithm that we have, it shows or requires a second na array. We can further improve it by performing an in place na heap sort, in place na max heap na sort by not using a second array. So there will be no longer external storage that is required. And of course, it will be useful on low memory devices. So this improved version of heap sort does not need any extra storage at all because we are performing in place. And let me show you how. And di ba we already have this max heap, okay? And what we do is we are going to swap 9 with 4, okay? And because when we do a remove the operation, this root na element will be swapped with the last na element in the heap, okay? And the last element in the heap is 4, so we swap it with 4, okay? And now 4 is on the root, and then 9 is the last na element, and we can now remove it. But in this case, we do not have a second array. We just have the 9 here already. Okay. Now, to maintain the heap no ordering, this 4 must be bubbled down because we want that the 7 is on the will be on the root because it's the max na heap. So when we perform bubbling down, so we swap it and then we swap it again because we must percolate it down. So now we have a correct na max heap. And if you check all the orders, so 7 is the maximum on this heap, 6 is the maximum. Okay. Now we now have a new sorted heap. So we can now remove the 7 again. How do we perform removing here? We must swap it with the last element. The last element is 4. So we swap, and the 7 has now been removed, and we are left with 4. Okay, now we must bubble this down again. We must swap it to maintain the heap ordering. So 4 is swapped with 6, and we now have a new heap. And the 6 is now the maximum. So what we do is we are going to swap 6 with the last element, which is 2. Okay, and swap, and we can now remove the 6. And we are left with this new heap, 2, 4, and then 5. And this is not correct, so we must maintain the heap ordering. So we must swap it again. And then we now have a swap 4 with 2. And sorry. So from here, we remove the 6. And then we swap 2 with 4. And then we swap 4 with 5 because 5 is the maximum. And now we have this new heap. And since 5 is the maximum, we can now swap it with the last element and then remove the 5. And now we have this new heap. The ordering is maintained because 4 is the max. And then we swap it again because 4 is the max. And then we remove 4 and we are left with 2. So as you can see, we did not need a second array. We performed a heap sort in place. So what is the running time of the heap sort? So in the pre-sorting or building the initial heap, we already know from the bottom of the construction, it could take O of n time. Then after building that initial heap, then for the heap sort, it would require then the O of n log n. So if we sum up O of n log n plus O of n, the dominant is n log n, right? So the big O is n log n. So why is this O of n log n? So every time we remove an element or the max element, it performs the down heap na operation to maintain the ordering. And we know that the down heap na operation is just at the worst case is doing the swapping for equivalent to the height of the tree, which is O of n log n. Okay, so for every node n in the heap, then we perform a remove min, which has a complexity of log n. So that is then equal to n times log n. So the complexity of heap sort is then n log n. So that's the end of this presentation. Thank you for listening.